In the last lecture, we derived the state space representation. We obtained the state space equations and the output equations from the differential equations of motion by linearizing the nonlinear differential equations about an equilibrium point. In this lecture, we will look at the solution of the state equations. To recap, we showed that the state space realization of a linear time invariant system is given by four matrices. So the state equations involving F and G and the output equations involving H and J. I also discussed and presented the concept of a state transition matrix, and in this lecture we'll look at the solution of the state equations. So again, to continue, the equations of motion for a mechanical system can be linearized about an equilibrium point. The linearized equations can be written in the state space form. So the state equations are of the form x dot equals fx plus gut. Okay, so the dimension of x is n by 1. So hence the dimension of f is n by n, and so the output equations can be written as y is equal to hx plus ju. The dimension of u could be m by 1, so hence g is n by m. The number of measurements or the outputs could be p by 1, so hence this H matrix is p by n, and the J matrix is p cross m. Okay. So if you assume that there is no direct term, basically the input u of t is not directly connected to the output y of t, then this j into u of t will be equal to 0. So u of t here means that the input u is a function of time. X dot is d by dt of the state variable x, and y here is the output variable. So for single input single output system, the dimension of u1t and y of t is 1 cross 1. So that's what single input single output implies. So the question is, can we solve these state equations? Okay, so this is a differential equation, first order differential equation with constant coefficients. However, this is a matrix equation, so there are n of these ordinary differential equations. These are also non-homogeneous because it is not only x dot is equal to f into x, but there is also a u of t. So let us look at solution of state equations. Before we look at the general form of n matrix equations at the same time, we look at a single ODE. If you have a single ODE which is homogeneous, it can be written as x dot equals ax. And remember, we are talking about linear time invariant system. Hence, this a is a constant. A is not a function of time. So this is very standard. It is very well known. What is the solution? X of t is nothing but x0 e to the power at, where x0 is the initial condition. If you have a non-homogeneous ODE, meaning that we have x dot is ax plus b ut, and again a and b are not functions of time, we can solve this non-homogeneous ODE, single ODE, and we can write it as x as a function of time is given by e to the power at x of 0, and then we have this term which is e to the power at integral 0 to t e to the power minus a tau b u tau d tau. So tau is a dummy variable which goes from 0 to t. Okay, so if you don't remember this, please go back and see any textbook on calculus or ordinary differential equations which you would have done, and you can see that this is indeed the solution of this. You can also substitute this back into this equation and convince yourself that this is indeed a solution to this non-homogeneous ordinary differential equation. So as I said, it can be easily verified that this is a solution to the non-homogeneous ODE by just simply substituting it in this differential equation. The extension to n by 1 state vector and the matrix equation x dot equals to f times x, where f is now a constant matrix, can be also now tackled. Okay, we can write the solution of this n by 1 matrix equation as x of t is e to the power ft into x of 0. So this is exponential of this matrix. So remember, f is an n by n matrix, x is a n by 1 vector. So hence x of t is some e to the power matrix, some exponential of a matrix f into t and into x of 0. We will see how we can evaluate or what is meant by e to the power ft very soon. So the exponential of a matrix, just like exponential of a constant, e to the power ax, is written by 1 plus ax plus a square x square divided by factorial 2 and so on. So here e to the power ft is given by identity matrix f into t 1 by 2 factorial f square t square and so on, and we can rewrite it in this form. The next term will be 1 by 3 f cube t cube. Okay, so the dimension of e to the power ft is n by n. Why? Because this is an n by n identity matrix. This is an n by n F matrix, okay, which we have obtained from the state space realization. F squared will also be n by n and so on. This can be written as f to the power k t to the power k divided by k factorial. The solution of the state equation x dot equals fx plus gu can be written similar to what happened in the non-homogeneous case. So we will have x as a function of time is e to the power ft x of 0 and then integral of 0 to t e to the power ft minus tau g u tau d tau. Okay, so previously in the non-homogeneous case e to the power something was outside, but then everything has been taken inside. So tau is a dummy variable which goes from 0 to t. We will denote e to the power ft as phi of t, capital Phi of t. So the solution of the state equations can also be written in terms of phi of t, which is nothing but x of t is phi of t into x0, 0 to t, this function phi of t minus tau g u tau d tau. Okay, so phi of t is an n by n matrix. So let us take some examples. So we'll start with a very basic and simple example. Let's assume that this matrix F has elements 0, 1, minus 2, minus 3. It's a 2 by 2 matrix. We can show that e to the power ft, which is the exponential of this matrix F times t, which is also denoted by this phi of t, is given by 2 e to the power minus t minus e to the power minus 2t minus 2 e to the power minus t plus 2 e to the power minus 2t e to the power minus t minus e to the power minus 2t minus e to the power minus t plus 2 e to the power minus 2t. So it might seem like magic. We don't know where we obtained these forms, but at least we can verify that this is indeed correct, but just by simple substitution. We will see very soon how we can obtain the exponential of a matrix. So if you want to find the solution of the non-homogeneous part, and let's assume u of t is equal to 1, then we have x dot is again f is 0, 1, minus 2, minus 3 into x plus 0, 1 u of t. Okay, and we are going to assume u of t is a constant. It is equal to 1. So once we do this, we can find the solution to the non-homogeneous part also, non-homogeneous ordinary differential equation, which is given by same thing as first part is same, 2 e to the power minus t minus e to the power minus 2t minus 2 e to the power minus t plus 2 e to the power minus 2t. This is the first column of this matrix phi. The second column is e to the power minus t minus e to the power minus 2t minus e to the power minus t plus 2 e to the power minus 2t multiplied by the initial conditions x1 of 0, x2 of 0, and the particular part, which is the non-homogeneous part due to this, is half minus e to the power minus t plus half e to the power minus 2t, and the second term or the second element is e to the power minus t minus e to the power minus 2t. Again, it's not yet clear how I got this, but at least you can verify that this is indeed the solution by simply substituting it. So we can take x1 of t as this, x2 of t as this, and then you can go back and substitute x dot, and then you can simplify and show that the solution x1 of t and x2 of t indeed satisfies this non-homogeneous ordinary differential equation, linear ordinary differential equation. So before we see how we obtain this e to the power ft, just quickly let's see some of the properties of this matrix e to the power ft, which I am also going to call phi of t. Okay, so first thing is phi of 0 is nothing but e to the power f into 0. So t equals to 0. That is nothing but the identity matrix. The inverse, which is phi inverse t, okay, is given by phi of minus t, because e to the power ft and 1 by e to the power ft will be e to the power minus f into t. Okay, so it is phi inverse is same as phi of minus t. We can also show very clearly and easily that phi of t1 plus t2 is nothing but e to the power ft1 into e to the power ft2, which is phi of t1 into phi of t2, and we can change the order because the if you have e to the power a into e to the power b, it is same as e to the power b into e to the power a. So then we can write it as phi of t2 into phi of t1. Likewise, phi of t, this matrix to the power n, it is nothing but phi of nt. Again, it follows from this expression. So if we have t1, t plus t plus t, so then again you'll have so many products of these matrices, and you can show that this is phi of nt. Lastly, you can see that phi of t2 minus t1, so I go from t1, t2 to t1 and then t1 to t0. So phi of t2 minus t1 into phi of t1 minus t0 is same as phi of t2 minus t0. Again, it follows from the fact that these are exponentials, and exponential of t2 minus t1 plus into exponential of t1 minus t0 will be exponential of t2 minus t0. And again, we can reverse the order. We can write this as phi of t1 minus t0 and phi of t2 minus t1. So e to the power ft, which is, as I showed you, is phi of t, is also sometimes called as the state transition matrix. Okay, this is a very important term in control theory, especially when we are using the state space formulation and we are analyzing a system using the state space formulation. E to the exponential of this matrix f into t is a matrix which is phi of t, and it is called as the state transition matrix. Okay, and these are some of the properties of phi of t. which I just now discussed. So the question is how to obtain phi of t in general. So I have showed you some examples where I said, okay, here is the solution. So the question is, where did I get it from? Okay, so we need to look at what are the ways to obtain this exponential of a matrix or the state transition matrix. So let's look at some simple methods first. So if f can be diagonalized, okay, so what do we mean by f can be diagonalized? We can convert from x to another state variable z, where x and z are related by x equals p times z. Then z dot is nothing but p inverse fpz. Okay, and as I said, p inverse fp is diagonal. So then we can write this as a diagonal matrix lambda into z. So what does this lambda contains? It is the diagonal matrix with elements lambda 1 through lambda n. So if you have a matrix F which can be diagonalized by a change of state variables, okay, a linear transformation of x to z. Remember, P is a constant matrix, it is a full rank, and P inverse exists. So then z can be written as e to the power this lambda t into z0, because what do we have? Z dot is equal to lambda times z. So the solution will be e to the power lambda t into z0. Okay, each term is like z1 is e to the power lambda 1 t into z1 0. Second term z2 is this, because the matrix, this is a diagonal matrix now. So hence, let's continue. So from x equals pz, we can rewrite x of t as p e to the power lambda t p inverse x of 0. So where did I get this from? So remember, x is p into z, z is e to the power capital lambda t z0. So x is p e to the power capital lambda t, okay, and then z0 can be written as p inverse x0. Okay, z of 0 is p inverse x0. So if you substitute all those things, you will get p e to the power lambda t p inverse z0. The solution of this x t can also be written as e to the power ft into x0, because what did we have? We have x dot is equal to f of f times x. So x of t is also e to the power ft into x0. So if you compare these two expressions, what you can see is e to the power ft is nothing but p e to the power lambda t into p inverse. Okay, and what was e to the power ft? This was the state transition matrix. So very simply, if f can be diagonalized, all we need to do is find out the diagonal eigenvalues of this F matrix, all the n eigenvalues, and then we do e to the power lambda t pre-multiplied by the matrix P and post-multiplied by P inverse. P and P inverse are the transformation which converts F into a diagonal form. If P can be written in the Jordan canonical form, meaning that some of the eigenvalues are repeated, then again we can find out what is phi of t, which is the state transition matrix, and the procedure is as follows. So we write again x is some p prime z. So remember, when you have a Jordan canonical form, the p which was used with distinct roots is not the same when you have repeated roots. So that's why I'm using p prime here. So we can have x is p prime z. So hence z dot is p prime inverse f p prime z. So p prime inverse f p prime is this Jordan canonical form into z. So the solution to this is z is e to the power j, which is that matrix which we get in the Jordan canonical form, into z0. And hence, if you go back and see what in terms of x, so x is p prime z. So hence x of t is p prime e to the power jt p prime inverse into x of 0. And again, comparing this with this, we can see that the phi of t, which is e to the power ft, is p prime e to the power jt p prime minus 1. So if the F matrix can be either converted into a pure diagonal form or into a Jordan canonical form, we can find the state transition matrix by doing e to the power jt or e to the power lambda t and pre-multiply by a transformation matrix P prime and post-multiply by a transformation matrix P inverse or P prime inverse. So let's see an example. So if F can be written in Jordan canonical form, so for example, this F has elements 0, 1, 0, 0, 0, 1, 1 minus 3, 3. This is picked up from somewhere, that arbitrary numbers. So the eigenvalues of this matrix are all equal, which is 1, 1, and 1. Okay, so hence this P, the matrix which will convert it into the Jordan canonical form, can be written as 1, 1, 1, 0, 1, 2, 0, 0, 1. Where did I get this? If you go back and see your notes, you can see if the roots are repeated once, then we have the second column is the derivative of the first column. So here it is repeated twice, so this is what you will get as P. And P inverse Fp is now given in this form. So it is not a diagonal, so the diagonal elements are 1, but then you have two off diagonal elements 1 and 1. So this is the Jordan canonical form, okay, after we do this P inverse Fp. So e to the power jt, j was the Jordan canonical form, can be written as e to the power t 0, 0, then t e to the power t and e to the power t 0, and half t square e to the power t, t e to the power t, and e to the power t. So this is basically in some sense similar to that we have repeated roots. Okay, e to the power t, the next one is repeated, so we'll have t e to the power t, then it is repeated again, it is half t square e to the power t, and so on. So e to the power t will become t e to the power t, and then finally we have only one term, 3 element, which is e to the power t. So e to the power ft is this p into e to the power jt into p inverse. And remember, we found out what was p in the previous slide. So if you substitute p and e to the power jt and p inverse, all of these are existing, you will get this reasonably complicated expression for the state transition matrix or the exponential of this matrix. So I don't want to go through each and every term, but the first term is e to the power t minus t e to the power t plus half t square e to the power t. It is straightforward multiplication of p into e to the power jt into p inverse, and then you find the 1, 1 term. The 2, 1 term is half t square e to the power t. The last term in the first column is t e to the power t plus half t square e to the power t. Okay. Likewise, if you see the 3, 3 term, it is e to the power t plus 2t e to the power t plus half t square e to the power t. So how are these obtained? You can use any computer algebra system or a tool to multiply all these expressions. So we have a p, which is a constant matrix. E to the power jt is this matrix containing exponential with time, and then p inverse, which was also known, and then you can multiply, simplify, and you will get these expressions for e to the power ft. So exponential of this matrix ft, where the matrix F had 3 repeated eigenvalues of 1. Let's look at another method. So this is the use of Laplace transforms. So remember, we showed you that we can write the state equations using the Laplace transform form. So e to the power ft was Laplace inverse of Si minus F inverse. Okay, so please go back and see the block diagram representation of the state equation written using Laplace transforms. This is what was mentioned there. Okay, so if I want to find the exponential of this matrix F using this Laplace transform approach, then I have to find Si minus F and the whole inverse, and then take the inverse Laplace transform of this. So let's take an example. So this matrix F is given by 0, 1, 0, minus 2. So the eigenvalues are 0 and minus 2. So here we can find out P, which is 1, 0, 1, minus 2, because remember the first element is 1 lambda 1, second element is 1 lambda 2. So we can find out the P matrix. Okay, so e to the power ft, we can go back and use the expression because these are distinct eigenvalues. So it will be P some e to the power lambda t. Okay, lambda are the two eigenvalues 0 and minus 2. So e to the power 0 and e to the power minus 2t into P inverse. So if you multiply this out and simplify, you will get 1, 0, half 1 minus e to the power minus 2t and e to the power minus 2t. So this is obtained from, as I said, P into e to the power lambda t into P inverse. Let us do the same thing using Laplace transform. So what is Si minus F? So S into I is SS and 0. So I is the identity matrix. Minus F is 0, 0, 1, minus 2. So if you simplify this, you will get S0 minus 1, S plus 2. So Si minus F whole inverse will be 1 by S. This 1 by S into S plus 2 and 1 by S plus 2. In this case, it is very simple. For a 2 by 2 matrix, we can find very easily the inverse in symbolic form. Okay, so these are standard methods in linear algebra. So we have the inverse of this matrix, Si minus F inverse, which is this. And then the Laplace inverse of this matrix, what is the inverse of 1 over S? That is unity. So remember, I had given you a set of common Laplace transforms and their inverse. So what about 1 by S into S plus 2? This you can also go back and see, it is half into 1 minus e to the power minus 2t. Okay, so S plus 2 will give you this e to the power minus 2t. So this is what is shown here. It is e to the power minus 2t. And when you have 1 into S into S plus 2, you can do partial fractions and then you will get this term. So as you can see, the expression for Laplace inverse of this is the same as what we got using P e to the power lambda t P inverse. Okay, so we can find the state transition matrix also using Laplace inverse. The third method is much more complicated, and I will go through it in brief. If anybody is interested, they can go and see this Modern Control Engineering by K. Ogata. Okay, this is a little bit more complex. So this uses two ideas. One is something called as a minimal polynomial and something called as a Sylvester's interpolation formula. So if you consider a polynomial of degree m minus 1, where lambda 1, lambda 2 dot all these eigenvalues, lambdas are distinct, then I can define a polynomial pk of lambda, which is in this form. So which is lambda minus lambda 1 dot dot lambda minus lambda k minus 1, lambda minus lambda k plus 1. See, lambda minus lambda k is missing here. And then lambda minus lambda n m divided by lambda k minus lambda 1 into lambda k minus lambda k minus 1, lambda k into minus lambda k plus 1 dot dot lambda k minus lambda n. So both of these, numerator and denominator, lambda minus lambda k or lambda k minus lambda k will be 0 is missing. So hence this pk, this polynomial of any lambda I, is equal to 1 if I is equal to k and 0 for I not equal to k. Okay, so you can see that the polynomial f of lambda of degree m minus 1 can be defined in terms of this pk. Okay, and that is k summation of k equals 1 through m f of lambda k pk lambda. And what does this do? This polynomial takes on values of f of lambda k at points lambda k. This is well known in, it is called as the Lagrange's interpolation formula. So what is f of lambda? This is a polynomial of degree m minus 1. So hence it passes through m points. So this is a little bit of background that we are going to use this notion of this Lagrange's interpolation formula in a special way to obtain the state transition matrix, or e to the power f, okay, t. So for the case of n by n matrix F with n distinct eigenvalues, for the moment let us assume that we have n distinct eigenvalues. So instead of pk of lambda I, we can find pk of this matrix. Okay, so this is very similar concept that we can substitute in any characteristic equation the matrix which gave the characteristic equations. Okay, so pk of f can be written as f minus lambda 1 into identity dot dot f minus lambda k minus 1 into identity, f minus lambda k plus 1 into identity, and f minus lambda m into I. So basically here instead of lambda we will put this matrix F. So some of you may have heard of this, something called as the Cayley-Hamilton theorem, which states that the matrix satisfies its characteristic polynomial. So basic idea is something similar there, that whatever is the characteristic polynomial, if you substitute instead of the eigenvalues, if you substitute the matrix, that also satisfies that. Okay, so here I can get a polynomial in which the elements are the matrices F, and again pk of lambda I in identity is identity if I equals k and 0 if I not equal to k. Okay, it follows more or less from whatever was happening to this pk of lambda, and whatever is pk of f instead of lambda, we now have the matrix F, which is in the state equations. So let us now define a function of this matrix F, which is given in this form, which is summation of k equals 1 through m f of lambda k, which we defined earlier, and pk of F matrix. This is called as the Sylvester's interpolation formula. This is in some sense is an extension of the Lagrange's interpolation formula. And this f function of this matrix F can be written in this form, which is this form here, and it is equivalent to this complicated looking expression, which is what? This is the determinant of some matrix. The first row of the matrix is 1 1 1, and this is identity. Second row is lambda 1 lambda 2 all the way, then f, okay, then f square, and all the way f lambda 1, f lambda 2, f lambda m, and then f of function of this matrix. Okay, so this function is equivalent to determinant of this matrix equal to 0. Okay, so if you are interested in the proof of this, please go and see some advanced linear algebra book. So what do we have? I want to find out e to the power f. I have done so much math and so much background, but eventually I have a way to find exponential of a matrix because this function f of capital F of this matrix, I can choose anything. Okay. So the determinant form of f of this matrix can be used to evaluate functions of a matrix. Okay, so any function f of this matrix F. In particular, we can use this determinant form to evaluate e to the power ft. So for evaluating the state transition matrix phi of t, which is e to the power ft, we set the last column in this form. So everything here remains the same, but this is e to the power lambda 1t, e to the power lambda 2t, e to the power lambda mt, and this is e to the power ft. And the last row is identity, capital F to the power m minus 1, and this determinant will be equal to 0. So what have we done? And we are looking at the case when the eigenvalues of this matrix F are distinct. So now I have a way to calculate this determinant. I have an expression which says determinant of something is equal to 0. And what I can do is I can evaluate this determinant by expanding about the last column. So basically I can say that I can expand about this last column and then obtain e to the power ft into something is equal to something. Okay, and hence using this form we can obtain what is e to the power ft, because this is an equation which involves many terms, but we can expand about this last element, and then we will get e to the power ft into something will be equal to something, and then we can solve for e to the power ft. Okay, it turns out we will get e to the power ft in terms of f to the power k, basically these terms here, where k equals 0, 1 through m minus 1. Okay, so this is a very complex way but very general purpose way to find the exponential of a matrix. This method of minimal polynomial and Sylvester's interpolation formula can also be applied when the roots are repeated. Again, I don't want to go into this. If anybody is interested, they can look at this Modern Control Engineering by Ogata, or they can look at some advanced linear algebra book. So just as an example, if the 3 of the roots are repeated, let's say lambda 1 is equal to lambda 2 is lambda 3, all others are distinct, then e to the power ft can be obtained by this determinant equation, which is determinant 0, 0, 1, and then some other terms, then 0, 1, lambda 1, then 1, 2 lambda 1 square. So where did I get this from? This is because lambda 1 is equal to lambda 2 is equal to lambda 3. It is repeated. Rest of the term is very similar. The term on the last column is different now, which is some t square by 2 e to the power lambda 1t, because it is repeated twice. Then the next one is t e to the power lambda 2t, and all the way till e to the power ft. Again, we have some determinant of something, very complex, many terms are there, is equal to 0. And again, by expanding about e to the power ft, this element we can obtain e to the power ft into something will be equal to something. Okay, and we can obtain this state transition matrix. To illustrate the method of minimal polynomial and Sylvester's interpolation formula, we take an example which we have seen earlier. The matrix F is given by 0, 1, 0, minus 2. The eigenvalues are 0 and minus 2. To follow this method of minimal polynomial and Sylvester's interpolation formula, we obtain this determinant which has these elements. So the first column is 1, 1 identity matrix. The second column is lambda 1, lambda 2, and this F matrix. The third column is e to the power lambda 1t, e to the power lambda 2t, and e to the power ft. So the determinant of this equal to 0 can be simplified by substituting what is lambda 1 and lambda 2. So we have 1, 1 identity matrix, 0 minus 2 F matrix, 1 e to the power minus 2t and e to the power ft equal to 0. So if you expand this, we will get minus 2 e to the power ft plus f plus 2 into identity matrix minus f e to the power minus 2t equal to 0, which will further simplify as follows. So we can take e to the power ft outside and put everything on the other side. We will get half into f plus 2i minus f into e to the power minus 2t. And this, if you substitute what is f, okay, then you can obtain as 1, 0. The 1, 2 element is half 1 minus e to the power minus 2t, and the 2, 2 element is e to the power minus 2t. So this is the exponential of this given matrix. And you can see and compare yourself that this is the same as obtained from method 2. The last one which I am going to discuss is a purely numerical approach to obtain the state transition matrix. This is by numerical integration. Okay, so the reasoning is the following. We know e to the power ft is phi. So now if you take the derivative of phi, so phi dot, what is the derivative of this matrix? Derivative of each term in the matrix. You will get f into phi of t. And what is the initial value? Phi of 0 is identity. So hence, if I know what is f, I have n square differential equations. So remember, phi is n by n. So we have phi 1 dot 1 1 dot is equal to some f into phi 1 1. Likewise, we have n square differential equations which we can integrate, and we can obtain the elements of phi of t numerically. So this can be integrated numerically using some code like in MATLAB. Okay, so this is a way to obtain e to the power ft, which is phi of t, by solving this n square differential equations, and these are ordinary differential equations. Okay, linear because f is constant. There are many other methods which are available, which I don't want to go into this, but there is a paper which is available in this link, which is written by some Cleve Moeller and Charles Van Loan. He is a very well-known linear algebra person. So Golub and Van Loan, he is that same Van Loan. And this is a very interesting way of saying how to obtain the exponential of matrix. So he says that there are 19 dubious ways to compute the exponential of a matrix. And the Siam review is a very professional, very well-known journal. Okay, so this came out long time back, and it is 36 pages. Okay, so anybody who is interested in other methods other than this 4, please go and get hold of this paper and take a look at it. So what can we do once we have this state transition matrix? So basically, what do we have? Our state space is x1, x2 all the way till xn. It's an n dimensional. So x is an element of Rn. So what we can see is, if I start from a point near to this equilibrium point, we took the nonlinear differential equations and we linearized it about an equilibrium point. So if you start from a point which is x of 0 initially, which is maybe near to this equilibrium point, then the trajectory of this x is governed by this differential equation. X dot is f of x comma u. Okay, and what is the solution to this differential equation, which is x of t is the state transition matrix phi of t into x0, plus this integral 0 to t phi t minus tau g u tau d tau. Okay, so this is also sometimes called as a convolution. Okay, so what is this schematically telling you? That if I can solve this equation, which I can because I know how to compute phi of t, so then I should be able to do all of these. Okay, and then I can show you what is the trajectory starting at x0. So what is the x of t as a function of time as we go along, as we increase in time. So this phi of t comma x0 can be used to study the nature of the trajectory starting at x0. Okay, and this is conceptually important, that later on we'll see that we will look at these trajectories to look at things called stability. Okay, so the state transition matrix tells us what is the trajectory of the state variables, or what is x of t as we start from some initial x of 0 near to an equilibrium point and where it is going. So in summary, the solution of state equations can be given in terms of matrix exponential. The solution shows the trajectory of the system as a function of time. So basically it tells you how the states are evolving in time. So x as a function of time, and x are the states of the system. There are several methods to obtain matrix exponential for linear time invariant single input single output systems. I have shown you 4. I have indicated to you a link to a very well known paper where there are many other methods. This is a very useful concept for control system analysis. So this is a formal way of looking at what is happening to my system as time progresses. Okay, so given states, given f, given g, okay, what is happening x of t. So it will tell you how the system is evolving in time. In simple cases where f is a function of time, very simple cases, so f need not be constant, it would be some simple constant functions of time, we can still solve the state equations. Okay, I am not going to go into this in this lectures, but you can look at some control systems book, advanced control theory books, where they might be having examples where this f is a function of time. So this is for some simple linear time varying systems. I can still get a solution in terms of this phi of t.